Okay, in this one, let's do a computation. Let's take a 2 pi periodic function. In this case, it'll be the Sawtooth wave. Um, and let's compute the Fourier series of it, okay? So, the Sawtooth wave, how shall we define that? We're going to define it to be the function. So, we're going to do an example. Oh, sorry. And this will be the Sawtooth wave. Um, The sawtooth is going to be defined as the 2 pi periodic function that we get by extending the function f of t equal to t, which we're going to define on just the interval from 0 to 2 pi. Or actually, excuse me, from negative pi to pi. So define this on negative pi to pi, like this, and extend periodically. So if I draw you a kind of picture of what's going on here, the idea is that we've got this function, and if I draw its graph, maybe if this is pi, and this is maybe negative pi over here, just pretend, and then this is maybe 2 pi, no, that's probably not 2 pi. Maybe 3 more out, it's 2 pi, and then 3 more out, it's 3 pi, and then that's 4 pi. And then we go back out this way, so negative 2 pi, negative 3 pi. We're going to have a picture that looks something like this. It's going to be t between negative pi and pi, like this. And then it'll just repeat every 2 pi radians. So if I copy paste this green curve and just copy it every 2 pi units, I'm going to get something that looks like this. Like this, and then this. Yeah, and then this. This is what it means to extend 2 pi periodically. Okay? This is called the sawtooth because, in particular, if I was to sort of draw this picture by drawing vertical lines to connect these this curve here, you would see a pretty sawtooth looking wave there. Yeah? So that's a sawtooth wave. And what we want to do is take this 2 pi periodic function, and I don't like drawing those vertical lines because it offends my my sensibilities around the vertical line test and all of that kind of thing, because I've been thoroughly calculus 1 pilled, but whatever, okay? This is the sawtooth. It's a 2 pi periodic function. Let's compute its Fourier series. So let's begin by computing the a's. We're going to, of course, use these formulas here. Now, these formulas, okay, they tell us how to compute in terms of integrals. And crucially, okay, I want you to notice about these integrals. These are integrals around what are called symmetric intervals. They're symmetric about the origin, okay? So we can use the symmetry of our function to help us compute those. I want you to notice, in particular, this function is an odd function. It's an odd function. And what that tells you is that if we integrate that odd function over a symmetric interval, we get 0. I mean, just think about it. This is an odd function as literally pictured here. If you take the signed area from negative pi to pi of this function, you're going to count this part negatively, remember, and that part positively, and you're going to get 0. Okay? So that's true. This is an odd function. So in particular, we know that when we go to compute a sub 0, we are going to get 0. And that's because this integral is going to be 0. Do you understand? You can't respond. But if you said no in your head, if you don't understand what I'm saying, rewind a little bit. Look up, remind yourself of what an odd function is, and look at the picture that I've got here, right? Okay, so f of t is an odd function. That's good. That implies a naught is 0. But not only is f of t an odd function, the fact that f of t is an odd function means, this implies that f of t times cosine nt is an odd function. Also, because remember, an odd times an even, and cosine of nt is even, odd times even is odd. Is that clear? Because I can really quickly run through it. If you have f of negative t times cosine of negative, or n times negative t, right? If you have something like this, because f is odd, that's equal to, by definition, f of negative f of t. And because cosine is even, that's equal to cosine nt. But this is just the negative of f of t cosine nt. In other words, f of t cosine nt is odd. It's odd, okay? And that means that all these integrals, which are taking place over symmetric intervals, are also 0. They're all 0. In other words, in the Fourier series for the Sawtooth, all the a's are 0. And I'll note this, because integrals over symmetric intervals of odd functions are 0. All the coefficients a sub n are equal to 0. You don't need to believe me. You can go ahead and compute them if you want to, weirdo. Okay? But I've just saved you a ton of work. Okay? By using the evenness and oddness of this function. Okay? This is going to come in clutch in a lot of situations. Okay? So it's always good to have these little tricks on hand. So that does leave, though, the computation of b sub n. So let's do that. So b sub n, remember, is by this formula. I'm looking at this formula here. Maybe I'll just go ahead and copy that. It's 1 over pi times the integral from negative pi to pi of f of t times sine of nt dt. Okay? What's f of t on negative pi to pi? That's just t. Literally just t. So this is equal to the integral from 1 over pi times negative pi to pi. Let me just not talk and write. Can you just let me do that, please? This. T sine nt dt. How to kill this integral. There should be a 3-letter thing happening inside of your brain. Very good. Integration by parts. You remember it too, right? Integration by parts. Do I remember it? That's a good question. The sort of mantra. That's the word phrase I'm looking for. The mantra is the integral of u dv is equal to u times v minus the integral of v du. Okay, that's integration by parts. If we execute on that here, we're going to let u equal, you always want u to be the bit that reduces the complexity when you take its derivative. So that's going to be t. And dv is going to be the rest of it, sine nt dt. So that du is equal to dt, and v is equal to any antiderivative of that, which is maybe negative 1 over n cosine nt. So by integration by parts, this becomes 1 over pi times the integral of u times v, so that's negative t over n times cosine nt. This evaluated from negative pi to pi, like this. That's how it works with integration by parts, minus the integral from negative pi to pi of v du. So that's negative 1 over n, and maybe I'll make the negatives get married, 1 over n cosine nt dt. Hopefully I did that right. Great. Excellent. Superb. Next, we plug in pi and negative pi. And what we get is, yeah, no, this is good. We plug in pi and negative pi. And what we get is negative pi over n times cosine n pi minus what we get by plugging in the bottom thing. Now, there's a minus what we get by putting in negative pi. I'm noticing that it's like there's 3 negative signs happening here. So I think that ends up being negative pi over n cosine negative n pi t. Or n pi, my bad. T is already negative pi. That's interesting. Plus, and now we got to take the integral of this guy. An integral of that is going to be 1 over n squared, because 1 over n gets another 1 over n, sine nt, evaluated from negative pi to pi. Now you know any integer multiple of pi, when shoved into sine, gives you 0. So in particular, this term is going to die, I believe. And what we are left with is this expression here, which we can simplify. Oh, by the way, cosine is an even function. So I'm looking at this term here. Cosine of negative n pi is the same thing as cosine n pi. So I can get these two terms here married. They can marry one another. Oh, and the pi, 1 over pi here will kill the pi up there. Anyway, all this means in the end that we get negative 2 over n cosine n pi. Now, cosine n pi is kind of hideous looking. So I want you to think about it. What is cosine n pi equal to when n is 1? That's cosine pi. That's negative 1. How about if n is 2? That's cosine. That's 1. How about if n is 3? Negative 1. Then positive 1. Then negative 1. Positive 1. Negative 1. Positive 1. Etc. It's an alternating sign gadget there. In other words, this is equal to, I believe, negative 2 over n times negative 1 to the nth power. Negative 1 to the n is negative 1 when n is odd, and it's 1 when n is even. So I think this is the right gadget. And I would like you to simplify it in this way as well. Okay? Check that. I'm pretty sure I'm right. Yeah, this is great. Now, I have another negative sign here, too. Get used to it, okay? You're engineers now. That negative sign, almost. Sorry, that was a little much. You're not engineers by any means. Sorry. Let me scratch that. You're wannabe, whatever you want to be when you grow up. I'm sorry. That's what I meant to say. That negative sign and those n negative ones are going to get married and become negative 1 to the n plus 1 power. Okay? So that's the Fourier coefficient. And we've done it. We've computed all of the Fourier coefficients. So in particular, we learn that f of t, if you believe this story, which you should because I'm not lying to you, not exactly lying to you anyway, f of t is equal to the sum. So I don't have any a's. It's going to be just the sum, oh my god, the sum from n equals 1 to infinity of b sub n times sine of nt. And just to be clear, this right here, that's b sub n. Okay? And that's the Fourier series. Now, it should still feel mysterious. Like, how in the world could the sawtooth wave, which is what f of t is, how could that possibly be expressed as an infinite sum of sines? Well, let me show you some pictures, okay? And these are just taken from the textbook. You see in green, the sawtooth wave there. What you're seeing in this picture are what are called the first three harmonics. The n equal to 1 term, n equal to 2 term, and n equal to 3 term all added together. And you can see it kind of looks like a wavy sine type thing, sine-like thing, okay? And so you can see how this amalgamation, this superposition of three sines with various frequencies is giving us this an approximation to this 2 pi periodic function, but it's still kind of bad, right? It still doesn't look all that good. So what you do, of course, is you increase the number of harmonics. You increase the number of sines. And in particular, if you use the first 20 harmonics in the Fourier series, you get this picture. And you can see that's pretty dang good. In blue. The blue is the sum of the first 20 harmonics. Okay? The harmonics refer to the n. The refers to the n. So like the first harmonic is the n equal to 1 terms, the cosine together with the sine. But this is the Fourier series for the sawtooth wave. And the theory states that as n gets larger and larger and larger, this will get closer and closer and closer to the actual sawtooth wave, the green curve. Okay? You see interesting phenomenon, of course, happening at the discontinuities. And there is a question. Does it really, where does it converge? Does it converge to the tip of the sawtooth or the valley of the sawtooth? Which one? It actually converges to the halfway point in between. But anyway, I'll talk about some of these details in the last video, okay? But I'm gonna have to make that video later. So maybe I'm just gonna leave it here and then add on a video later tonight, okay? I'll upload these right now though. Okay, so long.